In in this session, we're going to shift gears a little and start talking about zero-sum games, which we have avoided so far in this chapter. We've discussed more cooperative games and yeah, games where the agents are trying to coordinate versus the competitive scenario, which we had discussed in the first part of the book with tabular methods. And actually, the technique we're going to look at to address zero sum games, or the one that's being introduced in the book, is a sort of pseudo tabular method that we had looked at a long time ago in the context of ordinary reinforcement learning. But the reason why the approach we're going to take in this games is quite different than the example so far is that the we're going to look at a class of zero sum games where some of the challenges we had with the multi-agent problem, where like agents are choosing actions simultaneously, is going to be avoided here. And that's because there is sort of a subset of zero sum games, which are turn taking games, where on any given turn, one of the players cannot make an action selection. Or, they can make an action selection, which is a trivial, like, no op action. Right? So there's like different ways of actually, like, for this really specialized case, you could have implementations where you have like a specific turn taking game. That's one approach. For to sort of fit it into the multi-agent framework we've had so far, you know, like you can also have game environment situations where in some cases a player sort of has to defer to the other player and can't make a move, but in others they could make moves simultaneously. So to be more flexible, we can just implement this like as a version where both players can actually move, but we effectively make it a turn-taking game by restricting the moves of one player to some, special move that doesn't do anything. But when we have these turn-taking games, we can think of the game state for any one turn as like just from the perspective of one agent. And with the appropriate, transformation of the state, there's a way to reduce this problem into something that looks like a normal Markov decision process with just like a single agent playing. That's what we'll get to with the sort of the self play aspect of this, where an agent is going back and forth from state to state, but at any time it just appears as though it's making an action selection in an environment. And like for these, and like this doesn't have to be the case for general environments, but for these turn taking games, the reward is usually sparse, meaning there is no reward signal until the very end of the game when there is, a particular agent has won and the other has lost. Because it's a zero sum game, by definition, we usually state the reward from the perspective of the first player. So we'll like designate arbitrarily like one player is player number one. So then that player will get some reward R. In a board game, it's usually like +1 when that player wins. And then because it's a zero sum game, the other player's rewards are always -1 times that. So here it would be like one player would get a reward of 1, the other would get a reward of -1. So because the players alternate, like I said, you can think of this branching tree as turns are taken, but really that is the same as when we look at normal MDP problems where we have this branching of states that goes from a single point, and we only have to worry about one set of action selections in any given state. So for the first part of this, we're just going to go back to looking at these problems from the perspective of ordinary reinforcement learning rather than the multi-agent problem, and introduce this technique of Monte Carlo tree search. Now, I have sort of a diagram to try to explain this a little better. So when we talk about reinforcement learning, we start out with tabular problems where this, you could imagine just this grid, I'm using the grid world as a toy, just a toy representation of what a state space can look like, where each one of these squares is like a particular point in the state space. So for tabular problems, we can look at all of the states and we can calculate a global solution which is exact. So, and these types of problems can be solved with value function methods where we try to compute a value for every state, and then all those values are interconnected with the Bellman equations, or the Bellman optimality equations, if this is actually an exact solution. And from that, you can derive an optimal policy to make action selections in the state space that lead to the highest possible reward. Then, here I've drawn it where the state space is finite and small enough where we could have an exact solution like this. But it's also possible that the state space is too large to get an exact solution. And then we turn to approximation methods, where here I've sort of drawn these colors to represent a sort of a crude approximation function that might group states together. You could think of these colors as representing parameters in the function approximator, but this could be any type of function approximator. It could be, it could be linear, it could be a nonlinear approximator, it could be something that just buckets states together and assigns them a value. But all of those forms of approximation have something in common, which is that the values that can be represented by the function are limited by the construction of the function, and they don't necessarily respect the distinction between all of the states. So given the limitations of the function, we try to have a function, hopefully, that can generalize values well, so that if it has a pretty good value, like for this state, that then maybe it's never visited these other states, but because the function is generalizing well, it's going to have a reasonable value for surrounding states. And this, when I like surrounding in a broad sense of like however the states are being represented in the function, here the states are like literally close together in this grid, but in a more abstract sense that this could be like close together in some representation space. Now, using some kind of gradient method, usually we take this function approximator and then we try to minimize its error with whatever the true value function is that we don't know, but we have a way of collecting data where we're sampling and trying to calculate a value, an estimated value of the true value function, and use that to then correct our approximation function to make it close to that. However, because it doesn't have this property where all the states are distinct, there's not really a guarantee that this method will work or will lead to an optimal solution. But in a lot of cases, it does a pretty good job anyway, despite those limitations. So even in the multi-agent problem, all the techniques we've been looking at so far are in the realm of approximation, where we're using some, usually like a neural network of some kind, to try to learn something that we can actually represent, even if the state space is too difficult to get an exact solution. So for Monte Carlo tree search, it fits in the realm of tabular methods, because like the exact solution, we are going to have distinct value estimates for every state. However, unlike both of these methods, it attempts to learn a local solution. So here, like, let's say this black square represents the state that we're currently in the problem. What MCTS does is it collects samples, transition state samples that are close to the state that we care about. We try to build up information around this state, and then at some point we're going to reach the edge of what knowledge we know. Like if we're traversing the state space and expanding out, collecting samples, at some point we'll reach a state where we don't have any information about it. And then we have to fall back to some kind of estimator for that state. That estimator itself could be some sort of neural network function that has been trained by some other method. It could be a method that just does random rollouts where it just takes random behavior until it reaches a terminal state, and then it averages the performance of that random behavior. But it's not going to give us an exact answer. Obviously, if we had a function that could give us an accurate value for this state, we wouldn't need to do this method at all, because we'd be more in the realm of having this this global exact solution. So the problem here is, like, we have to keep expanding this out and collect data, and over time, this tree, or like all these states that we're collecting samples from, may get large enough that we actually get an accurate estimate for the different branching points from this state. So the success of this method really depends on how efficiently we can collect samples, and how accurately those samples can represent like the action values that we care about. So again, so far this is the only method we've looked at where we only care about this localized solution around the state that we care about. But that's how this sort of Monte Carlo tree search method fits into the previous methods that we've talked about. So are there any questions so far about this, about the different methods and how MCTS fits in?
Don't think I have any question here between the tabular approximation and the Monte Carlo tree search yet.
Okay, that's good. So I have some more. I'll get into some more details of how the MCTS actually functions. But yeah, this is just showing how its connection to the tabular methods and global solution methods. Okay, so actually, the Sutton and Bartow book also covers MCTS, just like in this chapter. It's being discussed in the context so far of just ordinary reinforcement learning, where these open circles represent states, and then these closed circles are action selections. And this technique also is really only suitable for problems that have a terminal state, because usually when we reach the edge of our knowledge, so here that this is showing how the tree has been expanded with different simulations. So let's say, like, this is the state that we care about, and then we look at different hypothetical actions that could be taken, and we have some method of selecting those actions, and then seeing what state we transition into, and then continuing that down. Now, at the bottom here, like if we reach an action that's never been explored, we can take some policy. Now, if you don't know anything about the problem, it's probably just going to be the random policy. And then you use that random policy to then just explore this environment, with random actions until you reach some terminal state, at which point, like you see what the final outcome is. So this is not a great estimator, especially when you're far away from a terminal state, but it may be the best you can do when you don't have any information. But this whole method only works in the first place if the problem terminates. So it's good for these like board game scenarios where there's a finite number of turns. If you have a game where the game can go on indefinitely, if people take random actions, then this method will not work. But the idea is that once we reach this new unexplored action, we're going to follow, use a rollout policy to reach some endpoint, some outcome, and then use the information from that outcome to update all the states that were visited. Now, this is showing the tree after we've already collected data. So now, like, this point that previously was unexplored, now is going to be added to the tree with the data. Like, all these other nodes in the tree have already been added from previous traversals through the tree. But at the very beginning, we just start with this, initial node at the top, and then this rollout would have occurred all the way up here before the tree received before we've received any sample updates from traversing the tree. So yeah, this like MCTS methods kind of date back to the first early use of like this method is a lot easier for computers to do something with than like doing gradient updates with neural network functions is much more computationally intensive. But all this method requires is to have, a table of numbers and to update it as an average. And it's sort of in the realm of other heuristic methods for doing tree search. Now, there are other ways of doing tree search that involve like complicated heuristics to decide, where to prune the tree or, which actions are worth exploring. This algorithm is designed to be sort of agnostic to the problem that you're looking at. So, like you just have this generic rollout function, and beyond that, you don't need any special heuristic. If you happen to have any, that can be combined with this method, but it's not necessary. But the sort of origin of the name of this is, well, it's a tree search algorithm. And there was this other concept when you're collecting samples of data, where of having an upper confidence bound statistic on samples that you've collected. The idea is like, let's say like you want an idea of, what this value could be. Like this came up also when we looked at multi-arm bandit problems, where you sort of have a few options in front of you and you've collected data from each of them and you want an idea of which one is the best option. So you could just look at the data that you've collected so far and say, well, one of these actions has a higher current average. And, whatever has the highest average now should be your best guess of what the best action is. But in the case of something like a tree search, or where we're trying to not just know what the best action is, but also collect information to improve our estimate of the best action, we want to instead consider a heuristic which is based on our confidence in how in that action actually being the best. So this upper confidence bound statistic is going to take actions or samples for which we don't have a lot of data on yet and apply a bonus to those. So it's going to like artificially boost the value that we think certain action selections have. And the reason for that is because if we assume that the rewards or whatever the source of the average value that we're getting for this follow some normal distribution, which it may or may not, but under that assumption we have an idea of what the variance of our estimate is based on the number of samples that we've collected. So if we have very few samples of something, there's a huge uncertainty in what that average value actually should be, meaning that there's some chance that the average is actually much higher than we think it is. And here, as we're trying to collect more data, we don't want to miss out on potential actions that are good, because the whole point of this is trying to find the actions that yield, the highest value in the problem. Like we want to find the best possible actions. So, the whole idea in MCTS is to sort of direct the exploration of the action space into areas that we think have a good chance, like a promising chance of being good. And that's based on both the average that we've collected so far and also the uncertainty in not, in actions that haven't been explored yet. So, yeah, I think I already talked about these steps of how the algorithm works. But yeah, we start at the root node, and then eventually when you get to the bottom, If you reach a node that hasn't been explored, you have to, calculate a value, usually through a simulation, and that simulation could be a rollout of a random policy. But um, the the way this upper confidence bound element comes in is how we actually traverse the tree in MCTS. So the idea is that, we have this tree built up with the data that we've collected so far. And we have to decide where to go in the tree. And let's say, each of these actions have some estimate of how good they are. And the point of the upper confidence bound method is that you don't just traverse the tree in the area that has the best average, because then you could be missing out on a potential node that is actually good, but you just haven't collected enough data yet to know how good it is. So that's what we're going to use the upper confidence bound selection for, to balance this, actions that we know to a certain extent how good they are so far, with ones where we have a high degree of uncertainty about, and we're going to try to reduce that uncertainty. So this is the upper confidence bound statistic that's used in MCTS. So QSA represents the value in the tree of what we think this state action pair is. And to this, we're going to add this term. And this term has n is the number of visits to that state action pair, like the number of times it's been visited in the tree, which also correspond to the number of times we've had the opportunity to add new data to it. Because, every time we traverse through one of these, we're eventually going to reach an endpoint in the tree when we do a new simulation. And then the data from that new simulation is used to update all of the values up through the tree. So there's some constant used to control how much we favor this exploration term. This natural log term isn't that important. You can see that, even as n gets extremely large, this is going to grow very slowly. It's sort of in there for historical reasons. It makes MCTS more stable. But this is basically adding sort of like a term related to the standard deviation of if we consider the mean value here to be like a probability distribution instead of an exact value, then we're sort of adding a standard deviation to that to say, like, we can reasonably expect that this value could be as high as this. And then whichever of these state action pairs has the highest of this value rather than just the Q value, then that's the one that we select to traverse in the tree for further expansion. And another important consequence of this statistic is that if there's a current action which has no exploration at all, so like it's never been visited, then those actions are always selected, like, first. So you can't actually move on to a new level in the tree unless you've explored all of the unvisited actions. This is in normal MCTS. Now, you could see that may be a problem in an environment where there's a lot of branching, where like you actually have to explore each distinct action, because like if you have 100 or 1,000 actions, it's not really feasible. Like you'll never move on in your tree exploration, because you're going to have to visit all of the unexplored actions at least once. So that's where some of these other techniques come in, or ways of actually limiting the number of actions that we have to explore. But yeah, if the branching isn't too big, we can still use this method. Remember, like, we don't have to do an exhaustive exploration. So even if we have to go down like many levels, this is really only a problem if the branching factor is enormous. But it's still something to keep in mind. Then once we go through the tree, we update the values such that the visit count is just incremented up by 1. So that makes sense. So at every node in the tree, we're just keeping track of these statistics. We have to keep track of the visit count so that we can keep computing this average. Because the idea, just like when we have tabular estimation methods in reinforcement learning, this final update of the Q value is just it's just doing an online update of the average of all of the V's that have been collected. So like this is where when we get to a node state, or sorry, no, like yeah, any state in the tree is going to use this update. But yeah, if this is an unvisited state, then this V will represent some like the rollout estimator that we had from before. But this is just using the temporal difference update of like one step like temporal difference learning that we have in ordinary reinforcement learning. And yeah, like this is very similar to what we would do in just ordinary Q learning, except, we're only going to do these Q updates for things that are in the tree rather than in normal Q learning, you would do this update for the entire state space. But here we're just doing it for the part of the tree that we have traversed. Okay, so that, yeah, and this should also match what is written in the book for how MCTS works. This is just the actual, this is like another version of the diagram here, but this is just showing how, you only update the values in the tree that have actually been visited. And the function quoted here is this one. So this matches the one I showed in this slide here, but it just ends up being this online update of the average value. Here. And they also mention here in the book the exploration action. So this is that the upper confidence bound statistic method, where if there's no visits to a state, then it's always selected, and that's because this term blows up if n is 0, and otherwise it's just the action value that has the highest of this expression. So now this is as opposed to what we normally do in tabular learning, where we do epsilon greedy action selection, which is that we select the argmax of just Q without this term. But then in order to make sure that we keep exploring, we also randomly take, with some probability, we take a completely random action, right? So this is this alternative approach in the tree search to exploration, where we always select unexplored actions, and then otherwise we have this deterministic policy where, we're selecting just the straight argmax here. However, it's based on the n count rather than just the Q value. So, are there any questions so far about this? MCT, how the exploration works? There's this note here also that this form of action selection tends to be more effective if a relatively small number of actions can be tried in a state. But so this note is a kind of contradicts the like this introduction to what we're going to try to use this for eventually, which are problems, these like turn-taking games where there's usually a large action space. So that's why like eventually we're going to get to versions of MCTS that don't work with this sort of vanilla method of action selection, but try to, we're going to have to augment this with something. But for now, we can just consider this. And I'm going to introduce a game where this is suitable to use, because the action space isn't too big. Okay, so far, yeah, we've just talked about vanilla, just vanilla MCTS, not in the context of like a multi-agent problem. But point of this is eventually to get to multi-agent problem and these zero-sum games, but turn-taking zero-sum games. So we had previously looked at zero-sum games in the context of tabular solution methods, and there actually is like an exact solution method to solve, whether they are turn-taking or not, right? Like you can always take a turn-taking game and convert it into a non-turn-taking game by having this no-op action, right? That on every step, one of the players is forced to select. So for all of those variations of zero-sum games, we already have a solution method for this. If it is in fact a tabular problem. And there was this soccer game we had looked at earlier. And these minimax game, or sorry, these two-player zero-sum games have a unique minimax solution, which it's not always what you want, although often the minimax solution is what we're after when we talk about zero-sum games in any context, just because it's an equilibrium solution. The most important aspect of this is that it is a non-exploitable solution. And this solution, the way we sort of solve it, it's not exactly self-play because right, we don't have this turn-taking quality to this game. Like this little sort of like rudimentary soccer game is an example where the agents do select actions simultaneously. But there's one winner and one loser always. And because they select actions simultaneously, the minimax solution actually, like, you have to compute it using a method that accounts for both agents at the same time. Because if this was in fact like a normal turn-taking game, you wouldn't, like, you could probably solve it with a deterministic policy. If I show, this is just an example of the minimax solution playing against itself. But if we go to like this step, now we're at a point where like this sort of graphical diagram of the problem shows one agent with the ball, the other without the ball, but they're facing each other. And in this scenario where the agents are facing each other, the minimax solution actually is stochastic. So this is showing like the actual probabilities of actions. Here there's 5, possible actions for each player. And the minimax solution actually has a split between the actions. It's sort of represented here for the agent on the left, or sorry, for the red agent, it's a split between staying still and going up. And for the blue agent, it's a split between going right and going up. But yeah, this type of probabilistic solution is not something that you can get if you try to solve this without considering sort of the multi-agent quality of it, which is, so if you don't actually calculate this equilibrium solution, the minimax solution where, the agents are sort of stuck in this equilibrium where we wouldn't expect, like, we can see that they're winning and losing. This is showing the game statistics of this, where they're winning half the time, losing half the time. This is a totally, this should be a completely even matchup. If we instead train these agents like we're going to do with we don't have an equivalent version of this yet with approximation methods. This solution is computed using a value iteration method for game theory, which is something we can use to get an exact solution. But we can also compute other solutions, like this is an independent Q-learning solution where the agents just try to train independently and do well against whatever the current opponent is. And unfortunately, with this method, they're not able to learn the true minimax solution, but they can still learn something where their performance against each other is sort of at a stalemate. And then we can see that this this solution has a lot of success against a random player, for example. So it's not that this solution is worthless or anything, but it has very different properties from the true equilibrium solution. And we can see that if we look at training an optimal opponent against this particular agent. So here, like this, we're going to do this also in the context of MCTS. But if we take a problem like this is a two-player game, and if we fix the opponent, so here, like I'm constructing an MDP out of this with a fixed random opponent. So now, like if I fix the opponent, now, this is like a true MDP. So we could use all the techniques from reinforcement learning to optimize performance against this opponent. But again, that's not the same as finding the equilibrium solution, because the property of the equilibrium solution is that it can't be exploited by any opponent. And the difference here is that if we fix an opponent, we can optimize against just that one opponent. So here, like this is the performance of the random opponent, or sorry, of the random player against an optimal opponent. And this is like the best you can do, at least in terms of the discounted reward, against a random player, which is that, it wins 99.1% of the time. And, with this, in like 7.5 steps. And this is like really what it's optimizing here is the discounted reward value, which is like -0.5. Sorry, so this is like the true optimal, like -0.504. So yeah, okay. So this is that. Now, the thing is though, like once we have the solution, so now like we have this policy that we've calculated, which is the optimal policy against a random opponent. And it does as well as you can possibly do against a random opponent. However, now I can actually construct a new MDP, which is using now this policy. And what this function does, it says, okay, now I have this optimal policy against the random opponent. Now I can learn an optimal opponent to this guy. And here, this is showing now this optimal opponent playing against it. And we can see that it now is able to win half the time and draw half the time. This is like the best you can do against this opponent. And if it starts, you can sort of separate the statistics into different things. We can see more details about what's happening. But when this agent starts with a ball, it wins 100% of the time. And when the opponent has the ball, like the best, this is sort of the best you can do with respect to discounted reward, is that you can basically guarantee that they have no way of winning. So you can block them out if they start with the ball. If you have the ball, there's some behavior they do that can be exploited. And you can keep going with this. Like here is then learning an optimal opponent to this guy. And we can see now that there is some opponent to this, which also like can win reliably. This is showing it from the perspective of this player. So it is unable to win now against an opponent I've created for this player. And we can go on that any method that we use where we're training against a fixed opponent in this game, there's always going to be some other opponent that can exploit that. And the difference is that if we have the minimax solution, so here what I'm trying to do is I'm trying to learn an optimal opponent to the equilibrium solution that I calculated. And this is the optimal opponent. And like this opponent, right, this reward is basically 0. So the thing it's optimizing, it can't gain any ground on this opponent. Like it has a slight, like there's this win loss, but it looks like it's winning with a higher percentage, but really this percentage isn't what's important. What's important is this value, because it's possible that it wins more than half the time, but those wins may be slower than the losses. So then, right, this is using a discount rate, so you get more reward if something happens quickly. So it's possible that yeah, it may be able to win more than half, but at a slower pace, and then its losses happen faster, which is more negative reward for it. So this solution, the one that we learned with value iteration, is the only solution with this property that it can't be exploited. And you can only calculate this with a certain type of self-play that is actually accounting for the actions of both agents simultaneously. Now, if we have like turn-taking games, like the ones like something like chess or checkers or backgammon, because on any given turn, you don't have to consider right the other your opponent's moves until after like you've played. Um, there's none of this like simultaneous action selection. It's possible that you could calculate a minimax solution with this sort of back and forth like method where you keep optimizing against the opponent that has previously beaten you. So like if the game like the reason why it doesn't work in this soccer game is because I showed the minimax solution here, and the minimax solution is stochastic. See, like in order to be not exploitable, you have to take specific random actions in certain states. Like not every state is stochastic. Like in the starting state, the policy is deterministic. You can see like the optimal thing is just to take this one action for both players. And like all the methods we're going to look at, including MCTS, even that do this sort of self-play back and forth, they're actually only able to learn a sort of optimal solution that has deterministic action selection. So if we have a game like this that is not a turn-taking game, it wouldn't work. Most games where there is turn-taking don't have this property. Like you don't actually need to take random actions at times, but there's no guarantee of that. Like it just happens to be the case for a lot of these games that we look at. But the book, I believe earlier, had an example of I think it was in it's like that there was a discussion earlier in the book about the limitations of value methods and or the limitations of this. Yeah, so this was a topic that we discussed earlier, but the idea is that if you have any kind of value method, like MCTS is a value method, right? Because we're learning these value estimates and or these action value estimates at every state. And in order for a value method to work in this sort of like it in a turn-taking game or like any kind of game, we need a deterministic equilibrium to exist because the value methods are only able to represent these sorts of deterministic equilibria. Now, if you have a joint action value method, it's actually possible to calculate these minimax solutions, but when we have turn-taking games, the joint action value method is special because it gets collapsed down to just an action value method, right? Because in every state, there's only one agent selecting action. So we don't have this grid of action values. We just have a single like vector of action values for the one agent. And this is a contrived example of a game where even though it's a turn-taking game, right, in every state, only one of the agents is making an action selection in each state. This stochastic game is contrived so that there is an equilibrium solution to this, but it is not a deterministic equilibrium solution. And that means that a value method will never work. Just like in the soccer game, the minimax solution is, not is a stochastic solution. This also, the equilibrium is a stochastic solution. And when we do like a turn taking method, or like, this like independent Q learning, like something that you can attempt to do with a soccer game, where at any given moment, each agent, it's only considering, its own actions, that can only learn a sort of deterministic solution, and it's always going to be exploitable somehow. But we're going to look at, like, nevertheless, when we look at these turn-taking games, we're going to consider methods that really can't deal with this situation, but hopefully, like the game we're actually considering, that's not going to be a problem with this self-play method. So I'm going to introduce this environment that hopefully I'm going to add to this over time, or I'm going to try to use this. I just wanted like a simpler game than, something like chess is really complicated, has a lot of rules. So there's a game that I can explain it a little bit, hopefully, if people aren't familiar. But there's this game called Othello, which is pretty simple. This is like a very simple representation of the board, but basically there's a grid. I think it's an 8x8 grid of squares, and players are allowed to place their tile on the grid. So there's a white player and a black player. The black player goes first, and this, I'm just representing the tile colors with W and B. So the game always starts in this state, and there are only certain squares. So like a player has to place a tile that is adjacent to tiles that are already on the grid. So in the beginning, there aren't that many moves available. So actually, these moves are represented by basically the position on the grid where you can place a tile. So these are the possible moves. So I think what the rules are: a player can only place their tile adjacent to one of their existing tiles. I think. Oh, so we can see how this game plays out. So you can form, like, the other important thing about this game is that there's this function that you can use to find out, what moves are actually valid for a player to take. This will always be from the perspective of the player whose move it is currently. But if I actually turn this into a stochastic game, like in the general framework, I have to make it, conform to the stochastic game functions where, both players can move on each turn. So we can see, like, this is the game formulated as a stochastic game. We can see that there's this pass move here for each player, and there's also a function that checks if an action is valid. And the way it works is that if it's not your turn, then the only valid move is a pass move. There's also other cases where the pass move is a valid move, because there are situations where you are not able to place a tile on the board because of the constraints of, like, the rules of how you can place a tile. And then the step function will just, so the action again is like a joint action, even though it's a turn-taking game. So it's a tuple of the action index for both players. But because of how this, like, the move function in this game is always from the perspective of whoever the current active player is. So when I call make move, I just select the action for, like, the board state here also stores with it the current player, whether, black or white, but it just gets mapped to an index of 1 or 2. And then, there's also this function to check if the game is over, if it's terminated. Basically, if you place a tile that we can see what it looks like here on the board. So here, the black player, right, has placed a tile here. And the way the game works is if you sort of surround your opponent's pieces in a line, or I think it's in any direction, it could be diagonal as well, then you flip all of the tiles in between to your color, right? So here, like this W has been flipped to black. And then on the next move, the white player plays here, which then flips this to white. So now, and then on this turn, like the black player is able to move in this, in this corner. So I think, you can play. Yeah, we could actually check for any of these states what the available moves are. But as the game progresses, like the game doesn't have to end in 60 moves, but there are 64 squares. 4 of them are used up at the beginning. And then oftentimes a game will end with the entire grid filled up, or this is the final state of the game here. So this -1 means that the black player lost, because here is a zero-sum game. The reward signal is always from the perspective of the black player, and the black player lost because in the final state, the white player has more of their color taking up the board. And the reward for every step along the way is 0. So this is what this function just creates an episode of the game where both players make moves randomly. But because there are only limited available moves, this is at least checking the fact that when they play randomly, they're only selecting from valid actions, not just from any of the available actions. You can see I construct this is valid action function here. Right, takes the board, the current player, and then it checks whether this action is a valid move for the player that you're asking about on the board. So does this make sense to people so far? Are people familiar with this game and how it works? It has some similarity to Go, but it's like a simplified version of Go.
Well, yes, it makes sense, so for, the basic rules of Othello, I think.
Okay. And then this is like if you play randomly, I believe with random play at least, the black player does have a disadvantage. I don't know if they have a disadvantage with optimal play, possibly, but at least like this is just testing the statistics of how the outcome of the game with both players playing randomly. It is a lot of trials. I don't think this is just within the noise limit. If I run this again, we'll see that I believe it does stay about like this 5%. Or I guess it's like a 10% relative advantage for the white player. They play randomly. So then this game, another nice thing about this game is it's relatively easy to construct a feature vector out of this. All we have to do is take the board, right, which is, it's just 64 values, and we can represent black tiles with like a 1, white with a -1, and then empty tiles we can represent as a 0. And that should contain all the relevant information about the board. We can see an example here of like what the feature vector looks like. It's just, 64 values. So a lot simpler than something like chess, where we'd have to have a different, representation for every piece. So, using this, right, it is a zero-sum game, but again, if we go back to a method like we looked at in the soccer game with just like independent cue learning, even though this is a zero-sum game, we don't really have a great, like, we're not going to see the reward function like go up at all, right? Because we have both agents competing against each other, and they may not arrive at any kind of meaningful equilibrium. But it is something that we can try we may have actually similar results to if we just trained against a fixed opponent. Like the types of solutions we're going to get are similar to solutions if we did rounds of independent Q learning sort of disconnected from each other, where we fixed one opponent and trained one, and then we fix that one and train the other, and we alternate back and forth. It's just that with independent Q learning, that's happening simultaneously, and hopefully they arrive at something. So this method, even though it doesn't find the minimax solution, one nice thing is that it is able to at least learn something that does well against a random opponent. And there's probably a lot of opponents that it actually does well against. So we can try that here. Yeah, this is a value. So you can use any method for this. Like this is like independent. This is using independent Q learning training on this game. We can see I've sort of set up this training function where what it does is it does a round of training, and then it saves a version of the agents from before the training started. So after each round of training, it takes the new agent and then plays it against the previous version of the opponent, right? So we always have like an old version of both agents and a new version of both agents. So as a gauge of whether this is working or not, I mean, one method that you can use, which is pretty common, is to check in every, so often and see, is the current version of the agent better than the previous version if we have saved. So here we could see some of these messages, or this value method didn't work that well. This also kind of lowers the exploration parameter over time. So we start out with a value of 0.5, which means that the agents are taking random actions half the time. And then we could see here on this round of training, there was some success where it keeps track of its success. So during training, it keeps track of its success. And now it's possible that during training, right, like we would kind of expect if this is going ideally where they're evenly matched, that the performance should be close to 0, maybe. I mean, we can see here lots of cases of it deviating very far from 0, which means that, perhaps during one round of training, one particular agent was getting a leg up over the other, exploiting something that then maybe will reverse later. And then this number in the message is the performance of the agent against the previous version. The idea is that if its performance against the previous version is better than what it experienced, during training, then it's a sign that it's making progress. So, this ran for some amount of time, and we can see at the end of it, this is now testing the performance of this trained agent against the random policy. We can see, instead of winning 45% of the time, now it's winning 58% of the time. So that is, evidence that it certainly learned something. I didn't run this for particularly long, and this is a value method. We can also compare it to policy-based learning, where we had like this, again, it's still independent learning, but now we have like an actor-critic method. And we can see this. Now this, actually, I ran this for a very short time. This is only training on each round of evaluation before it checks the performance. This is only training for 10,000 steps. Like that's nothing. This is a pretty simple problem. So with very little training, this performance against the random policy is like winning 73% of the time. So that's already, a lot of success for very little training. Yeah, policy method, these other. Now, all these methods so far are just doing independent learning as if this is like, these are two distinct agents. But where we're headed in this chapter is where we can do some form of self-play, where there's really just one agent, but that agent is capable of flipping its perspective between the states, whether, it's playing as the white or the black player. So we already had a method of doing this, actually, this sort of self-play, which we discussed in the last session, which was parameter sharing. So if we do like an actor critic independent learning method, but one where we share the parameters between the two agents, we really only have a single value and policy function. But remember, parameter sharing only works here if the function, the input to the function is sort of egocentric to that agent. Or in other words, the information has to be relative to that agent. Because obviously, like if we have a single function and it's trying to optimize performance for the black player, and then it sees, something for the white player, it's going to evaluate that, whether it's good or bad for the black player. But now we want to switch its evaluation so that if this is a state which is really bad for the black player, right? But now we're evaluating it from white's perspective, it should instead view it as something good for the current player, which is the white player. And in order to do that, it really comes down to how we construct or like how we represent the state. So here, like this sort of egocentric feature vector construction, what it's going to do is do the normal feature vector update here, which is just taking the board and trivially, putting ones, -1 and 0 where the tiles are. But now there's this, like this happens to be a really easy state to flip. All we have to do is take the feature vector and multiply it by -1. Because then that board will, like let's say it's for, the white player, and it's something that looks good for the white player. But right, like the normal value function we have, if it's for the black player, is going to evaluate that as bad. But if we multiply it by -1, then all the white tiles become black. It now appears as though we have a board from the perspective of the other player. And right here, it's like we can, because there's two agents here, for the second player, for the white player, I'm just taking the board and making it appear as though all of the tiles belong to the black player instead. And that way, we can use the same value function for both, and we can do parameter sharing, which, should be able to learn more efficiently, although it's possible that you may need, because now we kind of have to evaluate more, like half of the state evaluations don't matter when we're not doing parameter sharing, because those are the states where, right, an agent only has one valid action. So it's possible. Here I tried training it with a slightly larger neural network, but with parameter sharing. And also this was also very fast, like only for 10,000 steps. And this performance actually isn't as good as the other one. I'd have to do more testing to see, how long this would take to train to actually get equal performance to that. But, it appears to be working. So, I mean, this is still working as well as the value function method, right? Even though we're doing parameter sharing. And the book discusses this as well, about these egocentric observations. So here's an example of that with like a game of chess, where if we're by default, evaluating like the white player, but now suddenly we want to evaluate the black player, we have to transform the board into a state where now it's like, okay, for the perspective of the function, this looks like a state where white is playing with the black pieces. So now we can evaluate this and not even tell the function that, this board has been transformed. It'll just look at it from the perspective of the white player, which it's been trained as. So that's, this sort of, in the case of Othello, this phi function is as trivial as just multiplying by -1. In the case of chess, it's a little more complicated because the board is actually asymmetrical. You have to rotate it 180 degrees. There's an example here of doing this. And then, yeah, like how this applies to MCTS is like a little complicated because you have to keep alternating how you do the evaluation, but I'm not actually going to go, I'm going to save this discussion of like this like specialized version of MCTS where we do self-play and instead look at a simpler way of doing things where, like I said, we can always take a multi-agent problem and convert it into an MDP by fixing an opponent. And that's what I'm doing here. So this function is going to take a policy function, and this policy will represent an opponent. And then, depending on whether that opponent is white or black, we can construct an MDP where the step function now takes our action selection, right? So we make a move, and then normally now it's in a state, if we're doing self-play, where the opponent now, we can flip the board and the opponent can make a move. But if we have a fixed opponent, I mean, well, first we have to check if the game's over from that one move. But if not, then we'll use this policy function to make a move with the opponent. And then we'll return eventually a board state that is still from the original player. So like if we're the black player, we would make a move. Then we're going to use the fixed policy to make a move for white. And then it'll be a state where we can then make a move again. So this will then turn this into an MDP. And by making these like alternating versions of the problem back and forth, we can sort of do this disconnected version of independence learning, right? Where we first optimize against one opponent, and then we optimize against that learned opponent, and so on and so forth. Sort of, it should end up having a very similar outcome to when we do independent learning. But another thing that, like, so here's showing, yeah, like these are just two like test MDPs I made where there's one version that is black against a random opponent and another which is white against a random opponent. The difference being, right, if you're black, you just start with the original board state. If you're white, you have to wait, like the initial state is different because you have to first wait for the action of the black player in the first move. But if we create these MDPs, we can actually do the normal version of Monte Carlo tree search on this, right? Like this is just assuming an MDP environment where we take these actions. So what this is doing, like in order to use this, we need to have this evaluation function. So luckily that is very easy. So this is what we call like a random rollout evaluation. But if we have this game, all we have to do is, if we want to do a random rollout, we just have to run an episode with the Othello game, which we can do, and to make it an even better evaluation function, we can do it over some number of trials. This is just taking a state, having both players play randomly from that state, and seeing what the outcome is. And the idea is that this gives us some information of how good the state is for one player or the other. Now, it's not great information, right? Because normally we don't expect the players to play randomly, but once you get further down into the in the game tree, it should give us information about like how close a player is to winning. So here is an example of doing this value estimate on the initial state. Right, so like this yields one value estimate per state, and this is showing for every move we can make from the initial state what this random rollout estimate is. And we can, do it. But then we can do the same thing. So from the initial state, there's only 4 valid moves. As we get further down, like this is an example of just taking a state from the episode 10 away from the endpoint and doing the same evaluation here. So now there's 8 different valid moves, and the board state is more complicated, but we can see some, separation between the values here. Like there should be some more accurate information here. Although, yeah, I mean here, like I don't know how. Yeah, like I'm not sure why this would have a higher or like a worse evaluation than the other state, because these states are basically equivalent to each other if we rotate the board. But it may just be that there's not enough samples collected for this. But once we have this random rollout function, we can do MCTS. So what this is doing is it's going, if I pick a depth of 100, that means that, like this is never going to, like this is a depth deep enough to get to the end of the game tree regardless, right? Because there's a maximum of 60 moves. And actually, it's actually for the one-sided version of the game. Like if I do run episode of this MDP, right? This is actually only going to be 30 moves, right, instead of 60, because it's only from the perspective of one player. So we don't even need this depth of 100 here. But I'm just passing into this is the evaluation function that I'm passing in, which is just doing this random rollout policy. So yeah, I'm just treating this like if I'm playing a random opponent, I'm going to try to use MCTS to do action selection against that random opponent. So this is like sort of a half step away from the full, like the self-play MCTS. But we can at least, see how it does against this opponent. So when I call this, it does these numbers, this number of simulations. And it builds up this tree. And that whole tree is used just to make a single action selection from the state after we've collected all of these statistics. So like these dictionaries that have been collected, this is collecting all the statistics about what happened when this state was visited. But so actually, like, because we're not computing a global solution, right? We're just computing a solution for this one state. We have to keep repeating this Monte Carlo tree search evaluation for every state. So it is kind of cumbersome to see how well this is doing because we have to repeat this like 30 times potentially for every game. We could see that if I do this with 100 simulations to this depth, and I'm also, right, this function is also like, it's doing a rollout for 10 trials also. So there's a lot of computation going here. So just to evaluate this one move takes 1.4 seconds as opposed to like a few milliseconds for a function. I mean, the advantage is we don't have any training with this, right? We're just running it from scratch. But it is quite slow to evaluate a single move. So in order to test this, so here I actually tested it, right? Like this is like actually running a full episode of this MCTS versus the random policy. With 100, so this took like a full, almost 40 seconds, right, to do a single evaluation. Now, the fact this is 1 means it did win. I'd have to run this a bunch more times to see, how reliably it's winning. But I'm guessing that it's possible in the early part of the game, the MCTS doesn't do a great job. But as you get closer and closer to the endpoint, the advantage of this over the trained solution is that this is going to adapt in real time to the state. And it's going to do these simulations from a state close to the endpoint. And from there, the state space is much smaller. So it has a much better chance of actually directly calculating what the optimal moves are as we get towards the end of the game. Whereas, the global solution that we evaluated with these independent learning methods, right, it's not able to like do any extra computation towards the end of the game to improve its performance. But another thing we can do in MCTS is we can actually pass, like if we had a value-based method that we trained, like the one we had earlier that had, much better than random performance success, we could actually use that value function as our evaluation function at the end of MCTS. So instead of doing like a random rollout at the end here, like we're doing now, we could use one of those trained value functions. And the idea would be that whatever its performance is normally, if we do MCTS with it, where we just use it as this, as our estimator, then we might be able to improve its performance over what we had without MCTS. And that sort of concept of using this whole thing as a way of just hopefully strictly improving a given policy or value function that we've trained is one of the main ideas behind like AlphaGo and the algorithms that sort of combine MCTS with other training methods that we're going to get to later. But, for now, even just this totally vanilla MCTS with random rollouts, like this is, again, running with only 10 sims instead of 100, right? So it ran like 10 times faster, as you would expect, but also seemed to have won the game here. And then I also tested it here against, so now I'm giving it not a random opponent, but this is the best opponent that I trained with independent learning. So this is the opponent, right, that won 70 or so % of the time against a random player. And we can see here that this, only with 10 sims, this is able to beat this opponent as well, which is not too surprising because like this is probably very far from something like a true minimax solution. It's always exploitable. And because MCTS is calculating at every state this local solution, it should be able to find the way to exploit any opponent with weaknesses like that. Because like so much of what matters in this game probably is occurring like towards the end once the grid has been filled up a lot. So this MCTS can always concentrate its computation on the state it's in. And once Othello, like we saw this earlier, like you can see what it looks like towards the end of the game. There are a lot of moves to consider like all around here, but the number of possible states is just shrinking and shrinking as the game goes on. So this is also, I mean, Go has some of this property as well. Chess doesn't really, because like the board isn't shrinking in chess as the game goes on. But in Othello, at least, this is something where MCTS would have an advantage towards the end of the game. But once we like all these Monte Carlo tree search functions I'm showing, these are just designed to work like up here. Like this is designed to work with an MDP, right? Like not a stochastic game. But the reason why this works is because we can always transform this game into an MDP by fixing the opponent. And then we can see, there's some good success at least against these policies. So what we're going to try to get to next time is this like self-play version of MCTS where we have a single tree and we don't have a fixed opponent and we actually have the tree play against itself. But that actually requires this sort of flipping of the state periodically. And in order to do this, we need a specialized version of MCTS that does this this transformation of the state on every other turn. And really, applying MCTS at all to multi-agent problems only makes sense in turn-taking games because we need to have this branching that occurs from every state. And if we don't have a turn-taking game, there's not like this branching doesn't work this way, right? Like we would have branching from both agents that are distinct as opposed to just branching from a single agent selection. So there is a very natural connection from this to the MDP version of the problem. And really the only thing we have to change for this version of MCTS I showed here to the self-play version is that we need a way of keeping track of the state, whether we're considering the state for player 1 or player 2. Because we have to flip the rewards, and the tree also has to know whether it's in a state for player 1 and player 2 in order to build up these estimates. So I think next time we'll try to get that, try to do this this self-play version of MCTS where we alternate. the state representation, and then maybe compare what the solution looks like to the, like, it should end up like producing a solution similar to the, yeah, I'm not sure whether its solution would look similar to the independent learning solution with homogeneous agents, or yeah, the one with independent agents. But this whole thing where we're using like the same evaluation function and we have a single tree is gonna have a lot of similarity to the training here with homogeneous agents, right? Because like, the whole point of this is that we have this egocentric representation of the state where we always flip it to be, so it's from the perspective like of one of the players only, so that we can use the same function for both. But yeah, so are there any questions about this so far, or where we're going next?
No, I don't have a question currently.
Okay. And if I use this Othello game because I think it's a pretty easy one to look at, compared to more complicated examples. But yeah, if anyone has another game environment or idea that you'd like to look at, you can let me know. Otherwise, I think I'm going to stick with Othello for the testing these different versions of the algorithm, and eventually we'll hopefully get to like a more complicated implementation that looks more similar to AlphaZero, where we combine MCTS with function approximation. But yeah, if there are no other questions, thanks for coming, everyone, and hopefully see you next time.